Hi everyone and welcome back to the channel. This is a problem from the US Olympiad. Can you find non-zero integers satisfying the equation? Pause the video if you want to give this problem a go, and when you're ready we'll go through the solution. We'll begin by expanding both sides of the equation and recognizing that we can cancel out the x cubed on both sides. We'll also now realize that each of our terms in our equation has a factor of y in it. And since we're looking for non-zero integers, we can divide by y, and so we have the following. And now we can recognize that we've just created a quadratic equation in terms of y. So if we bring everything from the right side to the left side, then we have the following. And now we can write this once more in terms of our quadratic equation. And the reason why this is of interest to us is because now we can look at the discriminant of the quadratic equation. So recall that for a quadratic equation, the formula tells us all general solutions to it. And the discriminant is this bit inside the square root. And the reason why we want to look at this is because if an integer solution exists to this equation, then this discriminant must be some square number. So we can look at our equation that has values a equal to 2, b equal to x squared minus 3x, and c equal to 3x squared plus x. And so substituting these all into our equation, we have the following. And we'll expand this to obtain x to the power 4 minus 6x cubed plus 9x squared minus 24x squared minus 8x. We can simplify this further and take out a factor of x, so we end up with x multiplied by x cubed minus 6x squared minus 15x minus 8. To continue further from here, we're going to need to factorize this cubic expression. And we can do that using the factor theorem. So the factor theorem tells us that if we can find a root of this equation, say r, then x minus r must be a factor of this polynomial. So by writing our cubic as a function and then looking at the value when x equals negative 1, then here we're going to get minus 1, minus 6, plus 15, minus 8, which all makes 0. And so we know that our expression must have a factor of x plus 1 in it. Now to generate the second polynomial, we can recognize that the first term must be an x squared, since this must multiply to give us x cubed. But by doing so, we would have created a plus x squared term. So to get to minus 6x squared, we'll need to minus 7x, since that will be our minus 7x squared term. That will also create a minus 7x as well. So to get to minus 15x, we can minus 8x. And then lastly, we'll have 1 times minus 8. And now we can realize that this quadratic equation here factorizes as x plus 1 multiplied by x minus 8. And so in total, our discriminant is equal to x multiplied by x plus 1 squared times x minus 8. Now recall that we're looking for values such that the discriminant is equal to a square number, but that includes 0. So immediately we can have x equal to 0, x equal to minus 1, or x equal to 8. And we can ignore x equal to 0 since the question has told us to find non-zero integers. And we can also realize that given that x plus 1 is always going to be a square number in our expression, it's possible that x multiplied by x minus 8 will be a square number. So we can say that x times x minus 8 is equal to z squared. And expanding this out and then completing the square, we arrive at the following. And now there are two ways to find the values of x which satisfy this equation. We can do it by writing 16 as the difference of two squares and then looking at its factors. Or we can recognize by observation that this is the same thing as doing 4 squared minus 16 is equal to 0 squared. Or the Pythagorean triple, 5 squared minus 4 squared is equal to 3 squared. And thus our possible values for x minus 4 can be plus and minus 4 or plus and minus 5. And solving these leads to the solution x equal to 0, 8, minus 1 or 9. So we found a new solution where x is equal to 9. And now we're ready to go back to our quadratic equation in terms of y using the values of x we've just found. So if we sub these all in, then we arrive at the following. And solving the equation when x is equal to minus 1, we find that y is equal to minus 1. For the second equation, we can factorize this as y plus 10 all squared, and therefore y is equal to minus 10. And for our last equation, we can factorize this as y plus 21 times y plus 6, and therefore y is equal to minus 21 or minus 6. And so we have 4 possible pairs to our equation, namely these ones written down.